Hi everyone, welcome to the webinar today. We are excited to share with you a presentation about how abiotic degradation can explain the rate constant for natural attenuation of chlorinated ethylenes at 3 study sites. And this is a part of the Microbial Insights webinar series that we do each month. And so we really appreciate your dedication and taking the time to join us today. And it is my great pleasure to be able to introduce the esteemed speaker that we have, and he's presented a few times over the years, or many times over the years on our webinar series, Dr. John Wilson. And I think Dr. Wilson really needs no introduction. We all know the important legacy he has given us in environmental restoration. He has such extensive experience in natural attenuation processes and bioremediation, and he just brings a wealth of knowledge. He is in a role right now as principal scientist at Scissortail Environmental Solutions, but he had a 35-year tenure as a research microbiologist at the US EPA. And during this time, he produced numerous publications and, as we all know, made incredible contributions to our field. And so I personally consider him to be one of the leading authorities and a great mentor for me. His research for the EPA was primarily on the natural attenuation of BTEX compounds, fuel additives, and chlorinated solvents, as well as in situ bioremediation of these compounds. He has over 60 publications, many of them we use on a routine basis, and he co-authored and edited the US EPA report that was titled Identification and Characterization Methods for Reactive Minerals Responsible for Natural Attenuation of Chlorinated Organic Compounds back in 2009. As we all know, Dr. Wilson is a luminary in our field, and it's always a great honor for us to have him speak on our series. Before I let Dr. Wilson take it away today, I just want to remind you all that this webinar is being recorded and it's going to be available on the resource section of the Microbial Insights website in the next week. I know many of you like to go back later and rehear portions or all of what Dr. Wilson said, so that will be available for you. And you don't have to worry about emailing us. You're automatically going to get a link for this recording, as well as a certificate of attendance that will be sent to you tomorrow following this webinar. So after Dr. Wilson's done, we're going to leave some time for questions because I know all of you appreciate his expertise. So feel free to type your questions into the GoToWebinar panel, and at the end, Marshall and I will work together to read these to you so that Dr. Wilson can answer them, and we'll go get through as many of them as we possibly can. So I'm going to go ahead and turn it over to you, Dr. Wilson, and thank you for being here with us today.
Well, Dora, thank you for the opportunity to share some of the exciting work that I get to participate in. I'm a co-investigator on 2 SERTA VSTCP projects. One of them is with David Friedman and his students at Clemson University to develop a laboratory protocol that actually directly measures rate constants for abiotic transformations. It's part of their project to develop protocols to quantify these transformation rates and understand the mechanisms of abiotic transformation in water supply aquifers. So Alex Ramos and Olivia Dunn are the ones that actually done the work. David's the one that organized it. Sort of collated it, and I want to warn you that these are unpublished and preliminary, and Clemson has the right to interpret their data and publish it as they will. So we're going to consider those at this point as personal communication from Dr. Friedman. And the other project is a sort of project led by GSI Environmental in Houston, Dave Adamson and Charles Newell and Shala Farhat, who are developing a tool that can be used by site owners to facilitate a transition, to justify and explain a transition of remedies at a site from active remedies to monitor natural attenuation. And so the data workup that I'm going to show was developed as one of the tools for this sort of transition assessment assistant. Unfortunately, this thing is not quite yet out on the street. Final stages of pulling it together and getting it to review for certified so they can publish it. Why would we want to account for a rate constant for natural attenuation along the flow path? Well, one of the tools in the startup transition assessment uses that rate constant to determine if it's appropriate to leave concentrations above the cleanup goal in place in a contaminated aquifer when you decide that it's time to shut down active treatment. We'll illustrate that application about halfway through the slide talk. Dora provided some information from their basically the compendium of rates, or compendiums rather, of magnetic susceptibility measurements that they've made on samples sent to them by you, their clients. And so I'm going to help use that information to help understand whether your site might actually have a prospect that abiotic degradation is important. Microbial Insights is also a way of reaching the group at Clemson to attain the abiotic transformation assay. I'd also like to acknowledge Mark Verrey at the Minnesota Pollution Control Agency. Mark has been a thought partner in this whole process for 2 decades now. The mineral magnetite has been shown to degrade these chlorinated ethylenes through a process that does not produce the productively dechlorinated ethylenes that we're sort of trained to look for. The biology, bacteria, and some abiotic mechanisms take PCE to TCE to DCE to vinyl chloride to ethylene. Magnetite doesn't go that way. It tends to produce oxygenated intermediates, and there's some recent work from Olivia done that shows it can produce acetylene, but it doesn't produce the dechlorinated ethylenes. That makes it hard to recognize that looking just at chemical data for concentrations of CVOCs in groundwater. We're going to presume that magnetite is the major player for these abiotic reactions, and so we're going to use a measurement of the magnetic susceptibility of the aquifer sediment as a way of estimating the content of magnetite. And we'll use that as a way of ratioing and comparing rate constants that come from the Clemson microcosm studies to rate constants that we would expect to see at field scale. A lot of this was pulled together and figured out by Todd Wiedemeyer, work done for CertiP STCP some years ago. It's based on the observation that magnetic susceptibility, which is basically it's the property of getting material to act like an induced magnet, is a good measure of the quantity of magnetic materials. And within half a log or so, that holds together, and the relationship extends over several orders of magnitude. So what that means is you can put a magnetic susceptibility meter, a probe, a sonde, down in a PVC well and actually measure the magnetic susceptibility of aquifer sediments in a vertical profile. This some work was done by Rick Edwards at Jacobs Engineering on one of our study sites. It just kind of shows you what the probes look like in the process of putting it in a well and then interrogating the earth with electrical signals to measure the susceptibility. These are data that was produced by Todd Wiedemeyer comparing the vertical distribution of magnetic susceptibility at one of our sites to measurements that were done on core samples at the same location that were taken back to the laboratory and measured with a conventional laboratory magnetic susceptibility meter. And it tracks reasonably well, certainly to a useful extent. Let me back up real quick. The two dotted lines are the upper and lower screen on a monitoring well. So what Todd did is he compared the estimate across the screen for monitoring wells determined by the in-field down-well magnetic susceptibility zone to the estimates that are determined by averages of core samples collected adjacent to the well or collected during the well installation. You can see that there's really not much of a bias. One predicts the other pretty well. So we can measure magnetic susceptibility and predict the amount of the active agent in aquifer sediment with conventional in-well tools. So let's see what this can do to inform us about the behavior of these materials at field scale. Two of the sites I'm going to talk about today were fire protection training sites. Basically what the Air Force did is they burned up a circular pond, flooded it with water, floated off-spec or waste oils on top of that, set it on fire, put it out, set it on fire, put it out, to train their firefighters and to document the effectiveness of their firefighting procedures. And then after they were done, the stuff soaked into the earth. And so at this particular site in upstate New York, I am at the Fire Protection Training Site FT002 at the former Plattsburgh Air Force Base in upstate New York. It's about, oh, I don't know, 30 miles south of Canada on Lake Champlain. So those activities contaminated a water table aquifer, carrying chlorinated solvent contamination and BTEX for approximately a mile down gradient. And so this is the distribution of total CVOC contamination before they began active remedy. So you can see the red dots are the most contaminated, greater than 1,000 micrograms per liter. And then the orange dots is 1 log lower. The tan dots is 2 logs lower. And the yellow dots are couldn't detect it. And so the plume occupies a surface area extending roughly a mile down gradient from the source, moving underneath airport infrastructure, airbase infrastructure at the facility. So this is one of the tools. It's a beta version of one of the tools being developed by the GSI folks. What it does is it compares on a log scale the concentration of total alkenes with distance along the flow path. And so you see on a log scale, it does tend to fit a log linear relationship fairly nicely. You can project a line through those data and see if there's a prospect that the concentrations would move past the base boundary at a concentration in excess of allowed by the appropriate regulatory authorities. There's a possibility that some of the reduction in concentration is due to being askew the centerline flow path. So what the tool allows you to do is go through and use professional judgment and say, well, I'm going to take out the lower concentrations there that probably aren't really truly that center line, and only look at the ones that fit the higher boundary. And so that's what I've done here is I've excluded some of the wells. These are the wells that are left. And I'm comparing here the water table elevation isoplus against the distribution of wells as the plume moves from the source, underneath the runway, underneath the taxi, underneath an industrial area, underneath the golf course to approach the boundary of the former base. So if we fit a line through those center line wells, that's the rate constant for natural attenuation of total chlorinated alkenes in this aquifer on a per foot basis. And so the question is, can we explain that? Traditionally, this has been done by saying, well, it's all longitudinal dispersion. The people that are expert in that have re-examined that supposition and are not too happy with it. What they really think could be attributed to dispersion is a much lower number. So let's see if we can find an alternative explanation for that apparent first order rate constant for disappearance of chlorinated alkenes with flow along the centerline flow path. The assay developed at Clemson is actually, in my mind, a sophisticated advance in the use of carbon-14 assays. What Clemson does that's unique is they take their carbon-14 and they run it through a GC to clean it up, to separate the radio-labeled TCE or cis-DCE or vinyl chloride or PCE or whatever from the other stuff that was provided in a sample acquired from the manufacturer. And they only introduce the cleaned up radio label into the microcosm serum bottle. What this does is it gives them more sensitivity in detecting the accumulation of degradation transformation products. So they have a 160 ml bottle. They add roughly 100 grams of wet solids, 70 mils of water, and this purified carbon-14 compound, and then they add some more cold TCE or cis-DCE or PCE or whatever, incubated by slowly tumbling it in a tumbler. And then they measure using a scintillation counter the accumulation of polar degradation products. So they analyze the rate of accumulation of the radio-labeled polar products to determine a rate constant. And they have 3 experimental treatments for each sediment and each chemical. One treatment, the serum bottles are prepared in a glove box, and then the glove box headspace is sparged out with nitrogen to remove the hydrogen. So that's an anaerobic incubation. Another one is an anaerobic incubation where they add 2-propanol to scavenge up free radicals that might be one of the mechanisms involved in the degradation of the chlorinated solvent. Then the third treatment is same setup, except it's got oxygen in the headspace. These are some data from sediment at Plattsburgh that was analyzed using the Clemson assay. And so I've got upper left-hand corner, we have three different bottles. We're tracking the concentration of total radio-labeled polar products over time. So you can see that if oxygen is absent, the stuff accumulates fairly rapidly. If you look over to the right-hand chart, in the presence of oxygen, it still accumulates, but just not quite as fast. And then the lower left-hand chart, if you add that scavenger, seems like something starts and then it just is altogether precluded. So the scavenger somehow or other turns off this reaction. And so it's one clue that looks like an important mechanism. At least one of the important mechanisms involving magnetite is a free radical based mechanism as opposed to just a direct electron transfer. So these are the rate constants, first order rate constants extracted by Clemson for their sediment under anoxic conditions and aerobic conditions. So what I give you here is the rate constant and then the 95% confidence interval on that rate constant. You can see the Clemson assay has a 95% confidence interval. It's about, I don't know, 5 to 20% or so of the base number. That's actually a fairly tight number. The Clemson microcosm has a lot more water in it than natural sediment does. And so the magnetite or the reactive agent, whatever it is, in the microcosms has to degrade much more TCE or cis-DCE than it would if it were only degrading the cis-DCE that would be in a natural amount of water. So at a given concentration, because there's more water, there's more of the compound to be degraded. So at a given rate of degradation, the first order rate is actually slower in the microcosms. And so we correct for that simply by adjusting back to the rate constant that would be expected at a natural sediment to water ratio. And so that 0.32 per year in the microcosm actually is equivalent to 1.8 per year at field scale. And so these are the corrected rate constants and the corrected 95% confidence intervals. And then it turns out that the magnetic susceptibility of the material that Clemson selected, that I provided to Clemson to use for the microcosm study, is slightly different than that average across a contaminated interval in the aquifer, and so we do a correction for the amount of magnetic susceptibility to get a corrected aquifer rate constant. So those are the corrected aquifer rate constants and the 95% confidence interval on that corrected rate constant. If you don't have a headache by now, I'm going too slow. So we have a rate constant in terms of per year, but that field scale rate constant is in terms of per foot. And so we're going to convert the microcosm per year rate constant into a distant rate constant by dividing by the seepage velocity in the aquifer. I'm sorry, yeah, the seepage velocity of the groundwater along the flow path. At this particular site, best estimate of that is about 700 feet per year. So our K with distance equivalent to the Clemson microcosm study is 0.00173 per foot. And that actually is a little faster than the rate that we saw at field scale. And so we can say then that the abiotic transformation rate constant in the Clemson microcosms can account for that rate constant of natural attenuation from distance. We don't need dispersion to explain it. The whole thing can be explained fully by the ability of something in that aquifer sediment to degrade cis-DC, in this case, by transforming it to polar product. With this particular set, we can do an analysis of the 95% confidence interval on that distance rate constant extrapolated from the Clemson microcosm. We can say even a 95% confidence interval, the microcosm rate can explain a field scale rate. So I offer this as one way of validating and putting some substance to and trust in and make better use of this data that can be extracted from the long-term monitoring data at the site. This K with distance really is degradation. It's just not, well, the wells missed the plume or something weird. It's something that really is happening, a mechanism operating in the sediment to destroy the contaminant. As I said earlier, why would we want to know that rate constant with distance? Because we're going to use it in the transition assessment. So let's illustrate that for this particular site. The Air Force cleaned up the spill area, the fire training site. They spent a lot of your taxpayer dollars and did a pretty good job of that one. And then they did a somewhat less aggressive process of cleaning up the contaminated groundwater under the former Air Force base. And the system that was designed for collecting the plume reached a plateau in 2015. It actually reached a cleanup goal. And so what they had is they had 5 extraction wells up close to the source of the plume, and then a long collection trench that collected the down gradient portion of the plume, and then both waters, water from the collection trench and waters from the extraction well, were treated in a treatment plant. This is the concentrations of TCE, cis-DC, and vinyl chloride in water that was delivered to the treatment plant. And over time, you can see it's, I don't know, what is that? That's a little over 10 years. Goes from middle hundreds of micrograms per liter down to a concentration that was allowed by the state of New York to be discharged to surface water. So around 2015, the water coming to the treatment plant was clean enough that it could simply be discharged to surface flow. Now, these are the same data just for the last couple of years on a different scale to show you that this TC and the cis-DC actually got below and stayed below that discharge level permitted by the state of New York. So, I mean, the treatment plant is not treating anything. The water that's coming into the treatment plant is clean enough to discharge. They shut down the treatment plant. But here's the rub. One of the monitoring wells in the plume had concentrations that was much higher than that 10 micrograms per liter. order of magnitude higher. Is it safe to leave that concentration behind in the aquifer? So what the tool does is it takes that concentration, that's the green dot that's got the lines coming from it, and for that well projects the rate of attenuation, first order rate constant for attenuation along the flow path, and asks, does the concentration go below the maximum allowed concentration before the groundwater crosses the base boundary? In this case, it does. In fact, it projects the concentration to be about an order of magnitude below that required maximum allowed concentration at that point. So this shows that we can rely on these natural attenuation processes to finish the job and prevent contamination on site from migrating off site at unacceptable concentrations. You may want to ask, what about those other green dots? The Air Force has and is maintaining another set of treatment systems that are capturing and dealing with the down gradient portion of the plume. So this analysis only applies to that up gradient treatment plant. Okay, here's our second site. This one is at the former Twin Cities Army Ammunition Plant near St. Paul, Minnesota. Right at the northern edge of the facility, they had a plume of contamination move off the facility into a residential neighborhood. So what you see are the monitoring wells, 2 receptors of the plume, and some groundwater elevation isoplas. It's just a simple fine sand aquifer on top of lacustrine clay, fairly simple geology. And so these are the data on the distribution of total chlorinated alkenes along the flow path. So the blue squares and symbols are the monitoring wells, and then the yellow squares are actual measurements in the private wells that were the receptor. So I went through this process of weeding out the stuff that was askew the plume center line. So the filled blue circles were, in my professional opinion, the center line wells. And so this identifies those center line wells on the map. You can see they're embedded in and surrounded by other wells that were not identified as being center line. And we can project then a rate constant for natural attenuation with distance. You can see in this case that it actually might or might not. It is pretty close that it would clean up before it got to the before it got to the receptor. So Clemson has done a microcosm study for this sediment. So these are the corrected rate constants for anoxic material and aerobic material. Now at this particular site, for some reason, the aerobic material actually had a faster rate constant, 3-fold faster. However, the conditions I'm trying to describe is the distribution of the plume before they did a cleanup when the whole flow path was anaerobic. So I'm going to use the slower rate constant, the anaerobic rate constant, because it's the most appropriate description. And so that's the dotted black line, and it's close. That rate constant can largely account for the rate constant for natural attenuation distance. So that's 2 sites where that's held together and worked. If you use a 95% confidence interval on it, it's not nearly as tight as it was for the site at Plattsburgh. This particular site, the Clemson microcosm stuff is right on top of the central tendency of the Clemson microcosms, is right on top of the central tendency for the field scale rate. But this just gives you an idea of how much uncertainty there is in those comparisons to the rate constants. All right, the third site is not really a site because we're not done with it. So I'm going to warn you that this one does not have a Clemson microcosm study on it yet. It's in the queue and it'll be done shortly. This was a large plume of chlorinated solvents in the Ashmont Valley on Cape Cod, produced from a fire training site on the former Otis Air Force Base, now Joint Base Cape Cod in Massachusetts. If you look at that distance bar, this thing is about 5 miles long. So it goes off the base, actually underneath the kettle pond, works its way down into some cranberry bogs before it discharges to surface water. So this is a cross section of the plume. The Air Force installed 4 extraction wells, basically pump the heart of the system out and pump the down gradient toe of the plume out where it comes to surface water. So the filled red circles are centerline wells that I selected in my professional judgment to describe this particular site. And that shows that they're embedded in and surrounded by other wells that are contaminated, and then fairly well defined and prescribed by wells that are clean. So the Air Force did an acceptable job of delineating this plume. So this is the fit along the flow path. So that blue number is a first order rate constant for attenuation with distance, based on attenuation with distance in the centerline wells. Now, I told you that we didn't have a rate constant from Clemson, so I'm going to do something that I actually tell people in a journal article not to do. And that's take rate constants from other sites to try to predict the rate constant at your site. We've got an ESTCP product out, ER 2017-30, that collects rate constants for degradation of PCE, TC, and cis-DCE at a number of field sites and compares that to the magnetic susceptibility of the aquifer sediment. So those are the blue symbols that are not filled. And so there's a fair scatter of those, but you'll notice that many of them are sort of concentrated around a value of 3 times 10 to the minus 7 cubic meters per kilogram, magnetic susceptibility, predicting a rate constant of about 0.02. So I'm going to say, if I had to guess, based on the magnetic susceptibility at this site in Cape Cod, that rate constant of 0.2 per year would be the most plausible. And so if I divide that by the seepage velocity, it actually does a very good job of accounting for or explaining that rate constant distance. So I've got my fingers crossed that the Clemson microcosm study will come up with the same number. We're not going to count this as one of our 3. So we got 2 down and 1 to go. The third site is actually more typical of many sites where the plume was not really delineated adequately early on before they installed the remedy. And so they had treatment going before they really knew what the extent of contamination was. This is the OU3 site, Motorola 52nd Street site in Phoenix, Arizona. So this is under downtown Phoenix. You can see Interstate 10, you can see some of the runways from the Sky Harbor Airport. And so I'm going to talk about just this OU3, which is a rectangular area roughly 2.5 miles on each side. So the groundwater flow then is from from the right to the left. And as I said, they had a pump and treat system installed in one of the upgradient OUs. And so they started collecting data for OU3 at the same time that the upgradient portion of the plume in the other OUs was being treated. So I show you the extraction wells to the left, the capture zone of those extraction wells, and then the travel time under treatment conditions as groundwater should flow through this system under average hydraulic conditions. So these are data on concentration over time of TCE and for the wells in the upgradient portion of OU3. And it's a little bit confusing. Two of the system kind of hold together, but one of the wells concentrations go down and then rebound. And you can argue that the kinetics of attenuation are controlled as much by pumping a gradient of the OU as they are by natural attenuation mechanisms. Now, if you go halfway down the OU, you're some distance away from that in terms of distance and time of travel. These are the rate constants for these two wells, and they track each other fairly nicely. And then you go down to the toe of the plume for these four wells. Again, this is the rate constants for those four wells over time, or attenuation over time. And the slope of those lines track each other fairly nicely. So what we're going to do is evaluate the rate constants, the point rate constants for attenuation over time in those 6 wells, which are down gradient of the influence of the pump and treat system. So what we're looking at purely is concentration attenuation determined by the abiotic transformation processes, not influenced by pump and treat. So Rick Edwards and Jacobs did the downhole zone business with magnetic susceptibility. And so what I've done here is averaged the magnetic susceptibility measurements over the depth interval of this particular monitoring well, OU3 5M2. So we did that for basically all of the wells. These are 2 other examples of the screen and the variability of magnetic susceptibility in the interval across that screen. And this is in the far down gradient. What you can see is that magnetic susceptibility does bounce around in an aquifer. And so what I'm doing is comparing averages of magnetic susceptibility across a vertical interval to the rate constants in water acquired from that screened interval. So that's the red symbols. And I superimpose that over the blue symbols that I showed you earlier from other sites. And so what we see here is that this site in Phoenix, the rates are actually a little bit slower than what we've seen at other sites. And you'll notice that whereas the rates of attenuation in per year vary by about a factor of 2, the magnetic susceptibility varies almost an order of magnitude. So it's not a one-to-one relationship at all. That faded red square is the averages of the geometric means of the first order rate constants and geometric means of the magnetic susceptibilities. So here are data from the Clemson microcosm study. We get the same story. Pretty good reproducibility in the different bottles. Accumulation of polar degradation products from metabolism, abiotic degradation to TCE. And at this particular site, the anoxic rate constants were actually faster than the aerobic rate constants. Now this site has never really been anoxic. So I'm going to use the aerobic rate constant because the aerobic conditions are more representative of the conditions in the aquifer. Again, that's the slower of the 2 rate constants produced by the assay. So I plot the magnetic susceptibility of the material in the assay against the rate constant in the assay. Then that dotted red line is scaling it back down, it's just a linear projection. You can see that the rate constants, the slower rate constants of the Clemson assay can account for the rate constants that are seen in the aquifer system. For a while it bothered me that, well, if we've got more activity in the microcosm than we deserve, why doesn't it go faster at field scale? One explanation, one rationalization is that we may be seeing an effect of back diffusion. And so this is a declining plume. And so there's a possibility that the TC concentrations are being replenished and stuff back diffuses out of fine textured material. And so what that tends to do then is it minimizes or reduces the effective field scale rate constant. But anyway, we can easily explain and say that, well, there is a process operating in this aquifer that's consuming that TCE, and it does it fast enough that we can justify those degradation rate constants as being caused by a product of an abiotic transformation mechanism. So that's my bottom line. For those 6 wells, abiotic degradation mechanisms can explain the point rate constants over time in the long-term monitoring record. Now, what does this have to say for you? Dora provided me her recent catalog list of magnetic susceptibility measurements on work orders for work that you, the microseeds customers, had provided to her for analysis. And so I made the assumption that each work order was a separate site. And Dora didn't give me anything more than the number. She protected your confidentiality, so I don't know if each work order is a separate site, but that's a conservative assumption. And I gave you a breakdown of how many different numbers are involved in each work order. You know, half of them only had two or fewer samples. The average had 3 or fewer samples. 3/4 of them had 6 or fewer samples. So for each work order, I calculated the mean magnetic susceptibility, and then I just simply ranked them. Now you might ask, well, how variable are those means? This is the mean plus or minus the standard deviation. Some of those means were pretty wide, but most of them, well, largely because the numbers were fairly tight. So to just understand that solid progression of black lines has got about a half a log smear on either side of it. So where do our 4 study sites compare to all of the samples that you guys have sent Microbial Insights for analysis? And there it is. They're not exceptionally high in terms of magnetic susceptibility. Obviously, they're more than average, sort of in the upper, at least in the upper third or so. And so this would argue that if you have a magnetic susceptibility somewhere in the range of 3 times 10 to the minus 7 cubic meters per kilogram or more, you have a chance that abiotic transformations will explain natural attenuation at your site. So how do you basically sell the site owner that this is happening? One thing that I've done is just take dried sand or sediment from the site, expose it to a magnet, and you'll accumulate magnetite around the poles of the magnet. Now that clear plastic bag that's enclosing the magnet is there so that I can get the magnet away from the magnetite. If you don't put it in the bag, you'll never clean your magnet up. But it simply shows that the magnetic field imposed on the sand by the magnet attracts and orients the magnetic materials within that material. And you would be surprised how much magnetic material you can see in material that doesn't look like it's got anything in it that's black. A number of materials look like white sand, but if you put a magnet next to it, you pull out the magnetite. So that's one thing you can do. Of course, that's just a pretty picture. Look at it and see if it's their approach, but that could be used to justify a decision to send a sample off to microbial insights for analysis of magnetic susceptibility. The other thing that you can do is simply look at your natural attenuation with distance rate constant and see, well, is the cis DCE going away, but I don't see any production of vinyl chloride? In other words, is there evidence it's going away based on distance along the flow path, but no evidence that it's the biological dechlorination pathway? And if it's not biology, well, then you probably need to take a look and see if it's abiotic. And the best way, of course, to do that is the Clemson assay. So this is my message for today, and we do have a few minutes for questions, and I really find I learned more from the question and answer session than I think many of the participants. So I'm ready to talk to you about this whole concept.
Thank you so much, Dr. Wilson. That was an amazing presentation as always. We do have quite a few questions, so we'll go ahead and get started on those. How much magnetite do you feel that is needed for reasonable reaction rates? And is there a way to augment and add magnetite to help increase these rates?
All right, first answer, based on these 4 study sites, all of which had useful rates, if you've got somewhere around 3 or 4 times 10 to the minus 7 cubic meters per kilogram magnetic susceptibility, that's enough. Now, is there a way of augmenting it? No. That is roughly 1% by weight, maybe 0.5% to 1% magnetite. That's a bunch of material in an aquifer. 1% of an aquifer is a huge amount of material, and there's no way to blend it in. So this material is an important and useful agent for abiotic transformation as God laid down the earth, but that's not really the best way to add an agent. The best way to add an agent is to go with something like sulfidized 0-valent iron or something like that that has rate constants that are 1,000-fold higher.
Okay, next question is, when you're doing the magnetic susceptibility testing, do you have any concerns that the readings would be affected by impurities in the sand pack or bentonite, those types of things?
Yes, that's always an issue. One thing to watch is sometimes the workers will drop a tool in the well. You can see that as a spike in magnetic susceptibility that's orders of magnitude higher. You just simply delete that data from your average. Rick Edwards did a study of that question about the sand pack and actually measured the magnetic susceptibility of the sand. And that's probably the best thing to do. If you have access to the material that was used to sand pack, then measure it and see if it makes a difference. In his particular case, there was no indication that was a problem. What the sand pack tends to do is dilute your signal for magnetic susceptibility, causing you to underestimate the amount of magnetite. Now, the effect of that might be as much as reducing it by 20–30%. Another effect is that the tool measures volume magnetic susceptibility. In other words, it's the magnetic susceptibility of whatever is in reach of the electrical magnetic field produced by an alternating current. And so it also includes the empty angular space of the well. And so the fact that you're putting it into a hole in the aquifer, counting the hole as part of the signal, would cause the downhole tool to underestimate magnetic susceptibility to some extent as well. If you go back and look at some of the earlier data, you'll see that the error bars on this are plus or minus 30% to a factor of 2. So you don't get overly stringent in terms of interpreting a lot of this stuff. And the way you protect yourself is you take a lot of samples over an appropriate vertical interval and average them out and hope that the central tendency theorem will get you to a number that's going to protect you from error. Short answer is that's something to think about. You need to discount the fact of the contribution of artifacts caused by sandpacking material. Most monitoring wells are not sandpacked. Most monitoring wells actually allow the aquifer material to collapse against the screen. And so what you see is the aquifer against the screen, not a pack. And then finally, of course, you have to do this in a PVC well. You can't do it in a metal well because you're just measuring the susceptibility of the steel in the metal well. You can't do it with a metal screen, again, because all you see is the magnetic susceptibility of the steel in the screen. Okay, I'm ready for the next question.
Yeah, that makes a lot of sense. All right, the next question says, thanks, John. This is a really interesting topic. On the Clemson work, I wonder if you could concentrate or deplete the magnetite that was in those microcosm sediments, use a magnet or something to remove it, and then see what the effects would be on those observed rates.
That's exactly what Clemson is doing. The person to answer that question should be David Friedman. I will sort of channel him a little bit to say that, yes, we tend to see faster rate constants in materials that have, where they pulled out the magnetic material and enriched it in the sediment, and we see slower rate constants in the materials where the magnetic material has been pulled out. And so there is a rough association of rate constant with the quantity of magnetic material, but it's not linear. In other words, we don't get nearly as strong effect as we would expect. I surmise that what is happening is that the rate constant is controlled by the specific surface area of the magnetite, which means that the finely divided magnetite in the sediment has a preponderantly greater influence on the rate constant. But I also suspect that the fines are not as easily removed by the magnets. And so what Clemson is doing is they're pulling out the bigger chunks that have the less specific surface area and are less reactive. But the short answer is, yes, you can get an enrichment and a depletion of rate constant by enriching or depleting the magnetic materials in the sediment.
Okay, great. Next question is, can you speak to ethanes versus ethylenes using this technique?
Repeat the question, please.
It says, can you speak to ethanes versus ethylenes when we're talking about abiotic degradation?
Oh, okay. I have found no indication in the literature or in my experience that chlorinated ethylenes are subject to abiotic degradation by magnetite. It seems to be a property of the ethylenes, the ethynes. That's too bad, but that's the way it is. It doesn't help for TCA or 1,1-DCA. Also, we looked to see if it helped with PFO and PFOS, and unfortunately, it doesn't seem to do anything for that either. So it's good news for PCE, TCE, DCEs, and vinyl chloride, but so far as we know, not good news for any other contaminant.
This question says, thank you for the presentation. They have a general question that they're wondering if you can talk about what you consider to be the most important parameters that should be used to evaluate abiotic degradation.
Abiotic degradation is a wide field. It's under sulfate reducing conditions. You can also get a lot of degradation with iron sulfide minerals like bentonite. In that case, it's strongly controlled by the quantity and surface area of FES and also by passivation reactions on the surface of the minerals. That's over in one corner. You get very fast rate constants, but it's easy for something to come along and muck it up and make it work not as well. On the other side, on the magnetite side, the rate constants are much slower, 100-fold slower, but they seem to be very resilient. So really all you need to know is how much is there. And it does seem, however, though, that magnetite in one aquifer is a little different than magnetite in another. In some cases, we see faster rate constants under aerobic conditions. Sometimes we see faster rate constants under anaerobic conditions. So we really can't say magnetite's all you need to know about it. So the answer to the question today, August in 2023, is looking at your field data, your monitoring data over time. Does it look like something is making it go away? In other words, do you have an unexplained sink causing degradation of the contaminants along the flow path? And then if you do, can you associate it with some active agent? If it's a sulfate reducing anaerobic condition, that agent might be iron sulfides. But if it's mildly anoxic, iron reducing, manganese reducing, aerobic, it's almost surely magnetite. In which case, well, you can do the bit about putting a magnet in the sand and seeing if you get black dust on it. And if you do, well, then send it off to Microbial Insights for measurements of magnetic susceptibility. If you get a hit on that, then if it's really important to you to document it, find some way to get a sediment to Clemson for us, the C14 assay.
Okay. There are several questions trying to figure out ways to enhance the in situ biogenesis of magnetite, and there's questions about, can we add other iron minerals that might help to enrich or increase the aquifer magnetite content. So can you speak to your thoughts about that, if there's ZVI or other compounds that are added, if there's anything that we can do to help accelerate the process?
That would be a whole nother webinar. I'll see if I can say something useful in 2 minutes. It seems that the rate constants are related to the amount of iron 2 ferrous ion associated, sorbed to the surface of the magnetite crystal. And so if you're in an anaerobic iron reducing environment, you're likely to have magnetite that is more reactive. So one thing you could do is make it go anaerobic. And so a lot of these anaerobic biostimulation processes where we're adding vegetable oil is probably also inadvertently potentiating the magnetite reaction, making it go as much as 10 times faster. But that's the only thing that I can think of, is you change the geochemistry of the environment to favor the production of iron 2 in solution, which will make the magnetite more effective. In terms of adding magnetite itself, bacteria will produce magnetite from iron 3 oxides if there is organic matter in the aquifer. So if you have iron reduction going on, one of the products of that often is magnetite. In fact, geochemists can explore for and prospect for iron reduction processes by measuring changes in magnetic susceptibility with a meter that they fly over the land in a helicopter. So the bacteria could be producing magnetite from the iron 3 oxides if you give them an organic carbon source that allows iron reduction. And I think a lot of that happens sort of as a special bonus to try to create conditions favorable for D halocolloides action. But like I said earlier, if you want to really add something that's going to go after chlorinated solvents, if you're going to introduce the active agent, in my mind, it's hard to beat sulfadated zero-valent iron, nanoscale sulfadated zero-valent iron. It's 2 to 3 orders of magnitude faster.
That's very helpful. Can you talk about what makes magnetite unique in comparison to other magnetic minerals that may be present?
There are relatively few other magnetic materials and aquifer materials. The only one that's likely to be important is it's the mixed valent iron sulfide mineral. I think it's called greigite. To my knowledge, nobody's actually looked at them to see if they're reactive. It's a possibility that they're just as reactive as magnetite. It just hasn't been explored. But as far as I know, and I think anyone else knows, if you have magnetic susceptibility in aquifer sediment, what you're seeing by and large is going to be magnetite. That's the only stable, geologically stable mineral that has appreciable magnetic susceptibility.
Okay, 2 last questions on this. Did you have any CSIA data that you used in these studies? And if so, how did that correlate to looking at these abiotic trends?
We have the CSIA data. We haven't got the experimental process and protocol down to the point where the uncertainty is manageable. What we wanted to do is get isotopic enrichment factors for chlorine and for carbon so that we could look at lambdas for chlorine and carbon in TCE or cis-DCE in aquifer sediment and see if we could attribute the degradation to either the abiotic process associated with magnetite or something else. That's the goal. That was one of the purposes. That was one of the elements of the proposal of the Clemson project. And we're getting close to doing that, but we haven't done it yet. We do see at field scale enrichment in carbon isotopes. It's just that we don't have the equivalent studies done on pure minerals so that we have a benchmark to compare the field scale enrichments against. So we're trying to get there, but we're not there yet.
Makes sense. Okay, one last question for you. Do you know if this has been applied in bedrock systems with known magnetite present?
Well, there's some skepticism about it and a lot of controversy, but there is a site north of Los Angeles where this study was done on TCE contamination in a marine, I think it's marine sandstone, where there was magnetic susceptibility, and there's evidence from modeling studies that there is something making the TCE go away, and it's not explainable by the accumulation of biological products. So the short answer is, yeah, there is one site where they looked at that quite extensively. And I hope that when we're done with it and finished it with the material with the andesite, that it'll be accepted that what they're seeing is abiotic transformation of the chlorinated solvents carried out by the magnetic materials in the consolidated sandstone aquifer that's being studied. Short answer is yes, one site.
Great. That's information I did not know, so that's very helpful. Thank you again, Dr. Wilson, for sharing your vast knowledge. It always amazes me how much information that you have across, such a broad spectrum of topics. And so it's always a pleasure to have you speak on our webinar series. And I know that we had a good size audience today. So if you have additional questions about the presentation, please feel free to email them to info@microbe.com, and we will get with Dr. Wilson and get answers for you. And we appreciate you guys taking time out of your schedule to attend these webinars each month. And we really appreciate your loyalty and following in this series. And I know it's due to great speakers like Dr. Wilson today and all the information that we can gain. So if you have ideas of other topics you'd like to see, please also include them in your emails to info@microbe.com. Thank you again, John, for your help and for all the information you gave us. I really respect you and value your opinion and the contribution you make. So we are delighted that you took time to be with us today.
You're welcome. Thank you for the chance to talk with you.
All right. Have a great day, everyone. Thank you so much.